Hello friends, this is lecture number 3 of integral transformation. Integral transform. This is lecture number 3 of integral transform, and today we are going to discuss about Fourier complex integral. Okay, and if you want to follow me on Insta, this is my Insta ID ozalukizit123. And before we start, please subscribe the channel, hit the thumbs up button if you like my videos, and also share with your friends. Inspire me to create new contents for you. So now let's start. As we have already discussed about Fourier integral theorem, then in the lecture number 1, then we have discussed two different forms: Fourier sine integral and cosine integral. In lecture 2, links are in the description box. If you haven't watched yet those two lectures, then you can go through. Links are in the description box. And now we are going to discuss another form, that is complex integral, Fourier complex integral. So which is given by Fourier complex integral. This is given by f of x 1 by 2 pi. And what are the conditions to be satisfied by the function f of x? We have already discussed in the first lecture, right? 1 by 2 pi integration from minus infinity to plus infinity e to the power minus minus iux, integration from minus infinity to plus infinity f of t e to the power ut dt, and here it should be du. I missed that du here, so this is du, and this supposed to be positive, right? Just let me cut it, just wait. This is supposed to be positive. Okay, this is supposed to be positive, so let us keep that way. So now let us prove this. So in order to prove it, let me write the Fourier integral theorem that we have discussed in the first lecture, right? So according to that theorem, we have got f of x 1 by pi double integration from 0 to infinity and minus infinity to plus infinity f of t cos u into t to the power minus x dt du, which also can be written as 1 by 2 pi if you change the limit from minus infinity to plus infinity, and then you can write in this form, right? Okay, and also it can be written in this form as well: minus infinity to plus infinity. First let me write the functions of t dt, then again minus infinity to plus infinity cos u t minus x du. This is suppose equation number 1. We can write this way. Now, as we know, for odd function, we know that for an odd function f of x, integration from minus a to plus a f of x dx is 0, right? And sine function is odd function, so sine u into t minus x is odd function. So we can write minus infinity to plus infinity, integration of this function from minus infinity to plus infinity also equal to 0, right? So if this is equal to 0, then what you can write, if you multiply 1 by 2 pi and minus infinity to plus, integration from minus infinity to plus infinity f of t dt into minus infinity, integration from minus infinity to plus infinity sine u t minus x du, that gonna be also equal to 0, as this part is equal to 0, right? So, or we can write this way: 0 is equal to this way. So that means we have interchanged the sides, left hand side and right hand sides. We have interchanged because we are going to add these two equations, equation number 1 and equation number 2, and we're going to add f of x with 0 and the right hand side, this part, with this. Why? I'm going to explain it, just wait. So now if you add these two, then what you can have on the adding equation number 1 and equation number 2, we're going to have on the left hand side f of x plus 0. On the right hand side, what we can do here, we can do 1 by 2 pi common. We can take 1 by 2 pi common here. Let us take 1 by 2 pi common, and integration from minus infinity to plus infinity f of t dt, that part is taken as common. Then again integration from minus infinity to plus infinity, integration of this one plus this one, so du will be common, right? And this I should be multiplied with this one because I have not taken here I, right? Because this is 1 by 2 pi, not I by 2 pi. I is only here, so that's why I cannot be taken common, so that should be multiplied with the sine function, right? So hope you have understood this. And doing so, what we have got this one, right? So this is what we have got. Now let me copy this and let me go to the next slide. Okay, let me copy the last step and let me go to the next slide. Now let me tell you one more thing. As we know that e to the power ix, that is equal to cos x plus I sin x. So in order to obtain this form, we have done all these things. We have added equation number 1 and 2, and I have taken the sine function and the imaginary part. Okay, because let me go to the previous slide to explain this. So here you see, here we have cos, right? Then in order to get this e to the power, in order to get this 2, we must have I sin ut minus x with this. So then we can write this in this form, e to the power ix. That means in this two exponential form, right? So that is why we have done all these things. So hope you have understood this. So now let me go to the next slide again. So as we know this result, so we can write, if we apply this one with this, if we apply here this identity, then what we can have, we can write this one in this way. We get this result, right? So hope you have understood this. Now you see, let me clean this. Now e to the power iu t minus x, it can be written in this way, right? So let us separate the function of t. This is function of t and this is function of u, right? Then what we're gonna get, so just wait, we're gonna write this one with f of t, right? So doing so, what we're gonna have, this e to the power 1 e to the power minus I ux. So here we're gonna write du, and integration from minus infinity to plus infinity f of t e to the power ut, which is written with the function of t, f of t dt. That is what we have got, and this is the complex form of Fourier integral, right? This is the complex form of Fourier integral. So hope you have understood this. So let me write it here. Just wait. So this is the complex form of Fourier integral, right? So thank you for watching. See you in the next video.